Hello and welcome once again to this series of slide videos from the Cornish Radio Amateur Club. And today this is the first part of a number of slide videos on receivers. And specifically today we're going to look at receiver features. Particularly 6 receiver features. The first one is sensitivity. In other words, how good is our receiver at picking up weak signals? The second one is selectivity. How good is our receiver at picking out the signal we want and rejecting the ones we don't want? How selective is our receiver? The third one is bandwidth. If we're tuned to a signal, what is the bandwidth that we're able to provide to readily accept that signal and its modulation? It needs to be sufficient for us to get all the information encoded on the signal. The fourth one is frequency stability. How good is our receiver at managing to stay on frequency and not drift off and need frequent retuning? The fifth one is signal to noise ratio. Given that the HF bands particularly are very noisy, but putting that to one side and saying how much noise does our receiver introduce into the equation? And lastly, dynamic range. What's the range of this receiver? The range is from the very smallest signal that it'll receive to the very largest without causing distortion. And we'll be looking at that in a moment. Now, of these 6 features, some of them are related, or at least discussed together. One of them is sensitivity and signal to noise ratio. In order to compare like with like, we would normally say that a receiver has a certain sensitivity for a certain signal to noise ratio. In other words, we might say it's got a 0.2 microvolt sensitivity for a 12 dB signal to noise. Another two that are related, or at least discussed together, are selectivity and bandwidth. We've said that selectivity is our ability to pick up the signals we want and reject the ones we don't. And we've said that bandwidth is the receiver's ability to accept all of the signal we want without clamping it off and losing any of the information encoded as modulation on the carrier. So let's look at the first, sensitivity. We define this then as the weaker signal that will still give us a defined quality of output to the user. So we've said an example might be better than 0.2 microvolt for 12 dB synad. Now, synad, that means a signal to noise and distortion. So that means that the signal to noise is added to any distortion that the receiver may introduce. So this is comparing, if you like, with what goes into the receiver with the fidelity of what comes out, and takes 2 factors into account: any noise that the receiver adds to the equation and any distortion that the receiver adds to the equation. So, for example, if we had a quick look and said, okay, let's plot this on a graph, and we looked at the output of the receiver, we would see our typical noise grass floor. And if we assign that as an arbitrary value of 1, then in order to get our signal to noise plus distortion, we would need 15.8 times as much signal as noise. Why 15.8? Well, we're talking about signal power here, and if you convert 12 dBs into a ratio, you would use your calculator. You would type in 1.2 and then 10 to the x, and you would get the answer that ratio is 15.8 times. Why 1.2? Well, we're going back to the fundamental units of bells. We're going from decibels 12 to bells 1.2. So here we say that the sensitivity, if we put in a 2 microvolt modulated signal, we should get out a signal to noise and distortion of 15.8 times. The signal is 15.8 times that of the noise. So, how would we actually do that in practical terms? Well, that's what it might look like there on the right. You would see, for example, a signal generator producing a signal going into an amplifier, and out of the amplifier you'd be able to read the signal and the noise. So let's have a little look a bit more at the test setup. Now, this isn't needed for the examination, but it might help your understanding of what we're trying to do. Let's look at the test setup for this. If we had a signal generator with an inbuilt audio oscillator and we connected it to our receiver, out of the signal generator we would see a waveform a bit like that. That's an AM waveform, and what we can see there is the typical envelope waveform of AM. That is the carrier modulated in amplitude by the audio signal. And that could be, say, a 1 kilohertz signal, which would be somewhere towards the 1 or 2 kilohertz, might be towards the middle of the band of audio that we're passing. If we took the output of the receiver and fed it into an audio level meter, that would tell us the signal level. And that's what we'd expect to see there. The signal coming out of the detected signal, the demodulated signal coming out of the receiver back as 2 kilohertz, for example, and being fed into an audio level meter. And the more that we increase the level of the signal generator, the less noise we'd expect to see and the more signal. So there we are. Going into the audio level meter, we would see a combination of signal and noise, and that's the noise generated by the receiver itself. That's not noise coming in from the into the antenna port from HF signals from an aerial. That's just the noise generated by the receiver, because we've invested a lot of money in our signal generator and we consider that to be noise free. So there we are at the audio level meter. We've got the signal plus the noise. If we split the signal coming out of the receiver and feed part of it into a notch filter that is set to filter out our modulating audio signal, for example 2 kilohertz, then on the other side of the notch filter we'll just have noise. And if we read that into if we feed that into an audio level meter, then on the top audio level meter we'll just have noise only. So then this gives us the quantities to be able to work out what the signal to noise is. We've got signal to noise, signal plus noise at the bottom and noise only at the top. So if we subtract signal plus noise, subtract the noise only, that'll just give us a signal. And we've got the noise only, so we can work out our signal to noise ratio. So, the sensitivity then, the weaker signal that will give us a defined quality of output to the user. Let's look at selectivity now. Remember, selectivity is the ability of the receiver to select the wanted signal and reject the unwanted signals. Let's draw a quick graph of it then. If the dotted line up at the middle represents the frequency that we're tuned to, and we expect the wanted signal to be there. The graph on the left shows the signal power that's getting through the receiver, and the x-axis there is increasing frequency. Now, if we plotted a graph of the selectivity of our receiver, it would look something like this. You can see it's most selective on the frequency it's tuned to, and on either side it is rejecting signals. And if we draw some scale points in, if we say that at its most selective point, that is 0 dB, then when we're receiving half the power, we would say that's minus 3 dB, because we're dealing in power, not voltage. And we're going to draw another significant point in, that is the minus 60 dB point. Minus 60 dB because that is a oft used standard for quoting selectivity. So, looking at how that might actually be set up, and what setup we might use to read the selectivity and draw the graph, well, we could have a signal generator with a variable frequency dial on it, a VFO in it, and we would feed that into the receiver antenna port. And as we tuned from below the selected frequency to above the selected frequency, we would plot the graph, and that would end up as a blue graph of the received audio levels, and that would give us our selectivity profile that we've seen there in blue. So we've plotted the 0 dB point. That's the point when most of the signal is getting through. The minus 3 or half power points, and we've plotted the minus 60 points, and there's our curve. If we look down from the 3 dB points down to the frequency axis, incidentally, that gives us the bandwidth of the receiver, because the bandwidth is considered to be at the minus 3 dB points or half power points. But we're getting ahead of ourselves a bit there. We're going to look at bandwidth in a minute. We're still looking at selectivity. So, looking at the selectivity, if we then plot the difference between the center frequency and when we receive a level of minus 60 dB on our audiometer, then that is the selectivity of the receiver. And on this receiver, we say that the selectivity is 4 kHz. In other words, 4 kHz off center frequency, other signals are attenuated by 60 dB. And if you work out what 60 dB is as a ratio, it's 10 to the 6. 10 to the x. 10 to the 6 is a million. So we're saying then 4 kHz away from our center frequency, our signals, our interfering signals, are attenuated by 1,000,000 times. And that's a standard that's often used by transceiver manufacturers. Now, I represented that by a little red mark on the x-axis representing the 4 kHz, and we'll use that for comparison purposes in a minute. Now, if we didn't want to draw the whole graph each time, we just wanted to hook our receiver up to a piece of test equipment, how would that configuration look? Well, we would use 2 signal generators, one tuned to the signal of the center frequency, the desired signal, that's the top signal generator, and one tuned to the interfering signal, that would be the center frequency, for example, plus 4 kHz. And we would adjust these signal generators as we needed to. These would then combine in a power combiner so that we've got the 2 signals together and go into the device under test, in this case our receiver. And from there we'd go into a test system which would evaluate the output. And provided the test system determined that the interfering signal was less than, it was attenuated by greater than 60 dB, then our specification for this particular receiver would have been met. And we can adjust the frequency of the interfering signal with respect to the desired signal and see how that looks. In fact, how far do we have to tune away from the center frequency until we get that 60 dB attenuation. So that's selectivity, the ability to select the wanted signal and reject others on adjacent channels. And those adjacent channels will be either above the desired frequency, the center frequency, or below the center frequency. So the next slide, we're going to look at bandwidth. We've already covered this really. We've said that if we plot that curve and we look at the 3 dB or half power points and we project those down to the frequency axis, that's the x-axis, what do we actually have in terms of bandwidth where we're accepting the signal that we want? And that diagram I think shows that fairly clearly. And the bandwidth is the entire, it's minus from the center frequency and plus, so it's the complete bandwidth of the signal coming in. Remember that for selectivity it was from the center frequency to where you got the 60 dB attenuation, but bandwidth is either side of the center frequency. So there we have the bandwidth then showed on the graph, and this slide here is meant to highlight the relationship, if you like, or why we discuss bandwidth and selectivity together. There's our graph that we've been using so far. It's shown some bandwidth and some selectivity. The bandwidth in the blue column, and the selectivity in red. If we had a much better receiver, the graph might look something like that. You can see here that the sides of the graph are steeper and the bandwidth remains the same, but across the 3 dB points the top of the curve is flatter, and so it is more linear in its reception. You can see that the sides of the skirt are steeper, and therefore you can see at the 60 dB point from the center frequency out to where the minus 60 dB point cuts the curve, the selectivity is narrower. So that's pretty good. This graph here, similar sort of graph, but here we have a much sloppier curve. You can see there that the bandwidth remains the same. Across the top it's not very linear between the two 3 dB points, and at the bottom the selectivity is quite wide. So if you were going to purchase a receiver with one of the characteristics, the best one to buy would be the one in the middle, then number 1 on the left, and finally the one on the right. So that's a bit of a discussion about bandwidth and selectivity, and the filter shape is key, and I would urge you here to review, if necessary, the video on Q. So form factor then for these curves, and that will remind you then about selectivity. So just recapping on that one again, average selectivity on the left, if we were talking about them relatively, good selectivity in the middle, and poor selectivity on the right. The fourth receiver feature that we're going to talk about is frequency stability. Now, if you recall from transmitters, there's a phase lock loop, and the key to it all is the 6 MHz crystal reference oscillator on the top left. Now, what can we do to stabilize the output? The output frequency, as you can see, F out equals F crystal times N over A. So the crystal, N will be fixed and A will be fixed. These are essentially logic circuits which are not going to change. Those ratios are not going to change. But the crystal will change depending on heat, temperature, and on voltage. So what can we do to stabilize our transmitter? Well, we can use a crystal oven. That's very commonly used, where instead of having the crystal at an ambient temperature, it's in a small oven which is above ambient temperature, but it's thermostatically controlled. So you can expect from a crystal oven greater stability because the crystal is always at the same temperature. You can also work on having good stabilized voltage for your crystal oscillator. If you have poor voltage on the crystal oscillator, that will also cause frequency instability. Some people use GPS reference, and it is even possible commercially, it's very expensive, to use rubidium atomic clocks to provide very accurate references. But a GPS reference can be done at modest cost. Ultimately, the GPS signals are traceable back to USA national standards and therefore are very accurate. And some people use those to provide a 10 megahertz standard frequency to guide the phase lock loop to being accurate. So one point is made in the advanced book, and that is that the narrower the filter bandwidths in the receiver, and later on we're going to be looking at the superhead receiver and how intermediate frequencies make nice narrow bandwidths. The narrower the filter bandwidth, the more critical frequency stability is. So if the crystal starts to drift off on a receiver, then you'll lose the signal as the translated signal tracks past the skirts of the very sharp filter. So the fifth item we're going to look at now is signal to noise ratio. So the ratio of the strength of the signal carrying the information to that of unwanted interference. Again, this is when we're talking about receiver, we're looking at the noise introduced by the receiver itself and not by the HF noise coming into the receiver port, over which we have no control. We do have control over the noise introduced by the receiver itself, and there are various techniques to make this as low as possible. So we talked about sensitivity earlier on, and we said that better than 0.2 microvolts at the antenna port will give us, in an example receiver, 12 dB signal to noise ratio, signal to noise and distortion. And so that's what it would look like. It would look like noise power of 1 and signal power of 15.8, let's call it 16. And that would be considered the minimum discernible signal. Let's have a quick look at a setup on how we might look at measuring signal to noise on the workbench. Well, here we have it then. We have a signal generator which is producing an enveloped output. We have the receiver, we have the notch filter, and we have the two audio level meters. And we discussed that. This is exactly the same setup as we discussed in the slides on sensitivity, so no change there. And the final receiver characteristic we're going to look at is dynamic range. Dynamic range is all about the smallest signal to the biggest signal that you can usefully receive, and that's the dynamic range of the receiver. We could also talk about the dynamic range of individual components of a receiver. We could talk about the dynamic range of an RF amp or an IF amp, or indeed a demodulator. In other words, the smallest signal it can deal with up to the largest signal that it can deal with. And let's have a little look at this on a graph. This could be the dynamic range of a receiver. The output of the receiver will have some noise on it, even when there is no signal connected to the antenna. And that is the inherent noise of the receiver itself. And as we start to feed a signal in with increasing level, that's along the bottom, the received input radio signal, the output will increase steadily with increasing input. We will first discern the output when the radio signal exceeds the noise, and it will continue to increase up the flat part of that curve. But eventually the receiver will hit the top end of its dynamic range, and it will no longer increase the output linearly with increasing input. And because we don't have that linear translation of output to input, and rather input to output, then we're going to see distortion added. So let's have a look at some examples of dynamic range. There on the graph we have a spectrum analyzer display showing the noise graphs of the receiver itself and a tiny little white signal just poking up above the noise. And that would be, if you like, the minimum discernible signal. Once again, we would use a signal to noise ratio at the output to, if you like, pin it down and make it objective rather than subjective. So that might be, for example, a signal that has a signal to noise ratio of 12 dB. Then, as we increase the input on the receiver, the output will increase linearly until we get to the maximum signal with no distortion. And that's what it might look like on a spectrum analyzer. And then finally, we increase the signal beyond the dynamic range of the receiver, and because we're on the non-linear part of the curve, we're starting to see compression of the signal at the top. And instead of having a nice rounded top that you might normally see, you'll start to see clamping of the signal and distortion occurring. So then the dynamic range is between the minimum discernible signal and the maximum signal with no distortion. So that's the dynamic range of a receiver. And that gives us an idea of the receiver's ability to accept small signals and large signals without introducing distortion. So that just about sums up the 6 receiver characteristics or receiver features that are required in the RSGB advanced exam. In subsequent slides we're going to go on to look at subjects such as the super heterodyne receiver and noise. Thank you very much.